Good evening. Today we will go over two important quantities related to a vector field in 3 dimensions. So the so-called curl and the divergence of a vector field, I should say here, in 3D. So these there's going to be basically a generalization or at least the curl will be basically a generalization in 3 dimensions or an extension in 3 dimensions of what we did before related to the conservative vector fields. So it's a simple section in the sense that this lesson is quite simple because we just basically define these two quantities and go over a couple of examples on how to compute them. But as with all calculus related stuff, it's quite important, especially those of you in applied majors, to always remember the motivation and the meaning behind, physical meaning behind these concepts. And to make things easier, the name is pretty suggestive. The clue, so to speak, is in the title as to what something called the curl or the divergence measures. It's not obvious how to compute them until you see it. It's also not obvious what they are in fact. Are they actually real numbers or vectors? So let's get straight to the point, and then we're going to make connections with what we did beforehand. So the curl, so let's consider a vector. The main ingredient of today's class is a vector field in 3 dimensions, right? So you have f of x, y, z with the components given by 3 functions of 3 variables, x, y, and z. For convenience, so that we don't write so much, we can write p, q, r without always specifying of x, y, z, because we implicitly understand that's the case here. So the curl of a vector field denoted by like this. I'm going to actually give you the definition or the way to compute it in an expanded form, and then in another form that is kind of easier to memorize. So in a nutshell, we're going to write down immediately as a remark, it measures essentially the tendency of the vector field to rotate at a point, or in other words, to be more precise, the amount of rotation imposed by the vector field at a given point. All of these quantities, by the way, just to make it clear, are evaluated at a given point in the domain of that vector field. So you have that region in space where the vector field is defined, and at each point you can compute these quantities, the curl and or the divergence. So you might remember, just as a quick reminder, I'll write down later, but just right here in a corner here, remember from a previous lesson that we talked about the tendency or the amount of rotation at a point for a vector field in 2D, actually given by that difference between dp dy minus dq dx. And if there was no rotation, basically that means this quantity was 0, and that will indicate that that vector field was conservative. This basically measures the same thing, but for a 3-dimensional vector field, in which basically the rotation can happen in a generic plane of rotation. So that's basically the main difference here, right? So in 2D you have a single plane. Rotation is either clockwise or counterclockwise. Here the rotation, first of all, can happen in any plane at that point. There are lots of inclinations, so to speak, from your perspective. And then we'll see in a minute what, as a mathematical quantity, what's the nature of this curl. So actually it's a vector which looks at these possible differences between these partial derivatives over these components with respect to these 3 variables. So the curl of a vector field turns out to be a vector with the following first, second, and third component. So the first component is the partial r with respect to y minus partial q with respect to z. The middle component, dp dz minus dr dx. And then dq dx minus dp dy. And I should mention from the onset that actually it doesn't really matter the order of these differences in general. They are basically written in this specific order so that you can write the whole thing in a more logical or compact way, easy to memorize. Now, in my class, that's kind of not really relevant because, like I said, I allow, you can write this in the formula sheet. But just so you know, this actually comes from the so-called symbolic determinant, in which you can you have the first row just like in the cross product. Remember, the cross product can be written in terms of the so-called symbolic determinant, in which the first row is given by the standard basis in R3. In this case, the second row is also kind of symbolic, and it's given by the partial derivative operators, partial x, partial y, partial z, and the last row is given by the components of the vector field PQR. So the curl is defined in this way that is easy to memorize. It's really a symbolic determinant because it's not a real product, but if you follow the computation rule, if you follow the way you actually compute a determinant by expanding it via the first row, and you replace the multiplication with the application of the partial operator, then you come up with the components that I lay down on the left side of this equality. So for example, if you look at the first component, that comes from the second and third rows and columns, so it's going to be dr dy minus dq dz. The middle component will be dr dx minus dp dz, but with a difference of sign, because that's the second term in the determinant, so hence you have dp dz minus dr dx, right, in the I think I said it wrongly. So the middle one is dr dx minus dp dz with a sign change. So therefore dp dz minus dr dx in the middle of the component. So either way, you can write it in the formula sheet however you like, as a symbolic determinant, or expand it in the vector form. Just so you know that eventually you actually have to compute this vector if you have to find the curl. There is even in a more compact form that you may like. You can view, for example, this as a symbolic cross product between the gradient operator and the vector field itself, right? I mean, if you imagine that the gradient by itself is a vector of the partial operator, partial x, partial y, partial z, this determinant is basically the cross product between that and the components of the vector field. So that is the most compact notation for the curl of a vector field. And so let's write as a remark what it means, or what it describes. This curl basically measures the amount, I'm going to put this in quotation marks, of rotation at a given point. There are various intuitive descriptions. You could say the tendency or the amount of swirling of the vector field that creates at a point. If there is no rotation, then there is no curl. So the curl could be 0, 0, 0 if the vector field has no tendency to rotate at a given point. And let's see, another important thing to notice here, or to keep in mind, not to notice because it's not easy to notice, but to keep in mind, the curl is basically set up in such a way that as a vector, it's going to be perpendicular. So as a vector, the curl, let's write this down, is perpendicular to the plane of rotation and obeying the right-hand side rule, right-hand rule. Meaning that if at a given point you compute the curl, look at this picture here. Let's say you have this inclined plane and you curl your right hand along in the sense of rotation, the curl is going to be the vector perpendicular to the rotation plane, and it will point in the direction of your thumb, right thumb, if again the right hand curls the vortex, so to speak, in the sense of rotation. The magnitude of the curl, of course, indicates how strong the rotation effect of the vector field is at that point. And its direction will indicate the plane of rotation, because basically the curl is going to be normal to the plane of rotation. And with that, I think, well, let's establish one more definition and remark, and then we're going to get to an example, because I think it's also useful at this point to connect it with two-dimensional versions of it. So, if the curl at the vector field is 0 as a vector at all points, then f is conservative. There is no spin, remember, the same interpretation as for two-dimensional vector fields, also known as irrotational. And look at the analogy with the previous case, right? So remember, in two dimension, if I had, for example, a vector field given by two components, f of xy given by p of xy, q of xy, remember we established in the previous lesson that f is conservative if dq dx is equal to dp dy, or shall I say dq dx minus dp dy equals 0. So let's see how this is basically just a particular case of the curl being 0. I mean, this is basically the curl of that vector field, because remember, any two-dimensional vector field, I can view it as a three-dimensional vector field. So let's see how this connects. Let's say I want to actually view the same vector field in the plane. I want to elevate it to the rank of vector field in the plane, in the space, right? In which the first component just happens to depend on x and y. The second component happens to depend on x and y as well. And the third component is going to be 0 in this case. So r is going to be 0 because after all, it's just a vector field in the plane, but I just view it in the full space. So notice that if you look at the definition above at the curl, the first two components are all 0. Why is that? Well, r is 0, so all partials of r are 0. Q doesn't depend on z, so partial z is going to be 0. P doesn't depend on z, dp dz is going to be 0. R is 0, so it's going to be 0 minus 0. And only the last component is meaningful, dq dx minus dp dy, right? So if you write it in the standard basis notation, actually the curl of the two-dimensional vector field, but viewed as a vector field in 3D, is basically dq dx minus dp dy times k, right? Because you only have the third component. So obviously, you can imagine already, you know, the planar vector field. If you have a vortex in the plane, you're going to have a bunch of vectors perpendicular to the xy plane, depending on whether the rotation is clockwise or counterclockwise. According to the right-hand rule, they will point in the positive direction of z or the negative direction of the z-axis. So then why don't you live only with the curl, and you study separately the vector fields in 2D? The answer, as always, the most usual answer is convenience for the most part, right? Because if you have primarily two-dimensional vector fields to deal with, it's more convenient to not overcomplicate the situation and just deal with tool specifics to them. But if you take all the tools in 3D, then you have basically everything in 2D included, basically in that situation. Now there are, of course, tools that only make sense in 3D, right? Like the triple integral, for example, right? So, all right. So with that in mind, let's actually come up with an example to compute a three-dimensional curl in which we don't have these trivial entries, you know. So let's say f of x, y, z is equal to, and let's choose components easy to integrate because we don't want to overcomplicate anything so far. So let's say f is given by x plus y plus z, x plus y squared plus z squared. And let's say the third component is x squared plus y plus z. Okay, so this is P, this is Q, this is R. So the curl, let's follow the definition here. Partial Ry, or Ry, that's going to be 1, minus partial QZ, that's minus 1 minus 2z. Middle point, middle component will be partial P with respect to z, which is again 1, minus dr dx, that's 2x. Third component, dq dx is 1, and then dp dy is 1 again. So you see, in this case, it so happens that the curl actually has 0 vertical third component, so basically only the first two are non-zero, 1 minus 2, z1 minus 2x, and 0. Now, of course, you can still have points where there is no curl. So, for example, let's look at the point of coordinates 1/2, any y for that matter, and then 1/2 for z. So the curl of f evaluated at this point, if I plug in again 1/2 for z, 1/2 for x, and anything you want for y, we get 0, 0, 0. So that means if you are in this velocity fluid, for example, wherever you are located at these points, this basically is going to be a line, right? So 1/2 y, 1/2 as y varies. You should feel no vortex at that point, no tendency to rotate at that point. Okay, so let's move on to the next page and talk about the definition of the divergence, and then we're going to finish up with some examples and remarks. Okay, so all right, so one more time, let's take our generic vector field. So the divergence of a vector field is going to be this time a scalar, is a scalar that measures the amount of expansion or compression at a point caused by the vector field. So the tendency for the vector field, or the amount of or how much of the vector field actually comes in, the net effect, we're looking at the net effect basically of whether we have of how much comes in or out of a point, expanding out of a point. So let me illustrate briefly here. So for instance, you are at a point here on the vector field. Again, imagine you are in a force field, for example, or a velocity fluid. In some direction, a vector goes this way, some other, comes like this toward the point itself, another one like that, another one like this. So this basically measures the net effect of expansion or compression at that point. And the net effect, again, is going to be positive if it's going to be expansion and negative if it's compression. So the way it's defined. So the mathematical formula for the divergence, and again the notation is div of f, this time is a scalar, is simply looking at the cumulative size of the partial derivatives with respect to each coordinate. So dp dx plus dq dy plus dr dz. So and by the way, this one also has a formal notation. You can view this as the formal dot product between a gradient operator and the vector field itself. If you imagine again the gradient operator made of just the partial operators combined with the and dot with the vector field itself, but of course it's a symbolic dot product because you don't really make a product, you just apply the partial derivatives and add up the terms in the same manner you would do a dot product. Okay, so Gradient operator cross f will be the curl, right? Just to summarize, so gradient cross f will be the curl. Gradient dot f will be the divergence. Okay, one is a vector, one is a scalar. So again, it's important to point out that the divergence of f will always be positive if you have net expansion. If the overall effects of the vectors coming in and out that point is a net expansion, then the divergence is going to be positive. And if the divergence is negative, that's going to be if we have a net compression. And suggestive enough, I shall say, if the divergence of f is 0 at all points, then we say that big F is incompressible. Again, I hope the clue is in the title as to why we call it this way. So let's come up with an example. Let's do the example over the previous example we had when we computed the curl. And let's compute its divergence this time, and we're going to do another example in a minute. So the divergence of f is, again, this is p, this is q, this is r. So dp dx, which is 1, plus dq dy, which is 2y, plus dr dz, which is 1. So that makes it 2 plus 2y. So for example, what does that mean? In the plane, one meaning, right? In the plane y equals -1, the divergence is 0, right? If you are located on that plane, the divergence will be 0, so you shouldn't feel any pulling out or in from the vector field at that point. Let's do another example. So let's say I take f to be x squared yz, xy squared z, xyz squared. And let's do both the curl and the divergence. And this time let's do the symbolic determinant, right? So the curl of f, again, this is p, q, r, it's I, j, k, partial operators, p, q, r. And then we have dr, dy, that's going to be x, z squared minus dq, dz. So follow the determinant, minus xy squared. Let's see what we do here. So the r dy, give me 1 second. The r dy, yeah, okay, and then followed by the middle one is dr dx minus dp dz, but with the reverse order, that's dp dz, which is x squared y minus dr dx, which is yz squared. And then finally dq dx, that's y squared z minus dp dy, which is x squared z. Okay, so that's the curl. And then the divergence, dp dx 2xyz plus dq dy 2xyz plus dr dz, which is another 2xyz. So that'll be 6xyz. Right? So that's the divergence. So let me actually write down a couple of identities, and then we're going to talk about a little bit more on the conservative vector fields in 3 dimensions. So, for example, let's look at the curl of the gradient of a scalar field. you may want to pause for a moment and ask yourself what the answer is, because this is a very nice question. I mean, these types of questions are nice in general because they will force you to make connections with the previous topics. So any function you want, so take a function of a several variables, scalar function, right? Its gradient is going to be a vector field. So as with any vector field, you can ask yourself what is the curl of that vector field. So you can pause for a moment and think if you know the answer. And the answer is going to be 0. Now, why is the case? Because the gradient as any vector field, which is the gradient of a function, so automatically the gradient field is the gradient of a function, right? By definition, is conservative. Conservative means no spin, means irrotational. Since you have no spin at any point, you would expect the curl to be 0, the 0 vector at all points. What about another identity? What about the divergence of the curl of a vector field? So again, the question makes sense. Why? I mean, makes sense to ask mathematically. Why? Because f is a vector field on its own. The curl of f is a vector on its own. And so therefore the curl of a vector field, the curl of the vector field is itself another vector field. So it makes sense to ask what the divergence of it is. Again, you can use intuition. You could also use the math to actually prove this. Perhaps I'm gonna show you. Maybe we can show the proof here, just for the fun of it. So the curl. Remember, the definition of the curl is going to be. Let's actually use the index notation for the derivative because it's less to write. So ry minus qz, pz minus rx. Right? I just use the index notation for the partials. Qx minus py. Okay, so what is the divergence of that now? Now remember, the curl only has a non-zero meaning or a value if there is basically a rotation at a point. So the curl as a vector field on its own only encapsulates the rotation motion of the vector field. If you look at just the point where you have a rotation, there is no expansion. If there is a net rotation at that point, if there is a non-zero rotation at that point, there is no expansion neither in nor out around that point. In the limit, of course. This is very intuitive kind of stating it. So, of course, the divergence of the curl will be 0. Mathematically, it's also 0 to realize why that's the case. Because, for example, if I take the divergence of the curl, I take partial x of the first component. So I have ryx minus qzx plus partial y of the middle component, pzy minus rxy, plus partial z finally of the last component, qxz minus pyz. But again, assuming continuity and all of those good properties, remember the mixed derivatives, second order mixed derivatives cancel out. So the sum of this is 0. Okay, so the last part of the discussion is how do we actually find the potential of a vector field in 3D. Normally I don't put this in the test if I don't have enough time to go through it, but for the completion of the theory I think it's useful to do it. The mechanics is very similar except you have an extra step, but let's see it on the next page. Alright, so here's a question of the same type we had before when we dealt with line integrals. Given a vector field f, if conservative, check to see if it's conservative, and then if yes, find the potential. Find f of x, y, z, this time such that the gradient of f is big F. And then, of course, if you have a line integral over it, then you can use the fundamental theorem of line integrals, which, of course, makes life easier when you compute any line integral. All right, so let's start with f of x, y, z. By the way, none of the previous examples that we had was conservative because the curl was not 0. So let's look at the following example. Let's say the big F is given by x plus yz, y plus xz, followed by z plus xy. How do we check to see if it's conservative? We're going to compute the curl. Again, let's set up our symbolic determinant. Partial operators, and then the components P, Q, and R. All right, so hopefully you should see clearly that this is going to be 0, right? So let's start with drdy, that's going to be x minus dq dz is another x. The middle point, partial p with respect to z, that's y, minus partial r with respect to x, that's another y. Finally, partial q with respect to x, that's z, and then partial minus partial p with respect to y, that's another z. So the curl is 0. Therefore, f is conservative. So then I'm guaranteed there exists f of x, y, z such that the gradient of f is big F. In other words, I should be able to match the components of the vector field with the partial derivatives of a function of 3 variables, f of x, y, z. So how do I actually determine this? We go through the same process that we had in the previous class for 2-dimensional vector fields. You can pick any partial you want. For consistency, I always pick the first one. So partial x as a function of x, y, and z, set it equal to the first component, x plus y, z. And we find the potential by integrating both sides with respect to x. We're going to do a partial derivative with respect to x. So on the left side, we just have the potential, right? Remember, on the left side, it's the antiderivative with respect to x of a partial derivative with respect to x. So the two cancel each other, the two operations, so therefore you get the original function. But again, this is the detail that you have to keep in mind. On the right-hand side, we're going to do the antiderivative which, with respect to x, which is x squared over 2 plus yz times x. So let's just write it xyz. Plus a constant of integration, which, let's call it again k or c, whatever letter you want. But that can still depend on the other two variables that we didn't integrate. Okay, so again, if it's not clear, imagine you do partial x of the right-hand side. Whatever is in terms of y and z alone should disappear. Sometimes people are still not clear or confused on this step here because everybody is so used from calculus 1 to just adding a constant of integration, a constant being a real number. But let's not lose track of the fact that we are actually integrating a function of 3 variables. We do a partial antiderivative. So just in the same manner as anything in y and z, when you do partial x, that will disappear. When you go in reverse, you can't just assume that you take the constant of integration is just a real number. Basically, it's a unacceptable restriction, so to speak. So your original function via this integral at this stage of the game is going to be x squared over 2 plus xyz plus anything in terms of y and z. That's basically a constant with respect to x, essentially. So this is the potential, but of course that's insufficient information. We need to know what k of yz is, and we're going to eventually find that by matching the other two components. So now we take partial y of the potential that we just found and match it with the middle component of the vector field. Now partial y of this is going to be 0 plus xz plus I cannot use prime notation because that's still a function of two variables, partial y of yz. Okay, so this should be equal to the second component of the vector field, y plus xz. Okay, if everything is done correctly, anything that depends on x should cancel, left and right. If it doesn't, that means you made a computation mistake, or maybe, as it turns out, maybe the vector field is not conservative. So maybe you make a mistake when you computed the curl. Now, at this stage in the game, we have that partial k with respect to y of yz is y. How do I find k of yz? We're going to have to integrate both sides with respect to y. Now, keep in mind, this is still a partial derivative because we still have two variables, y and z, on the left side. So on the left side, we have k of yz, and on the right-hand side, we have y squared over 2 plus, and I hope you get the drill at this point, not just a constant, not just a real number, but something that maybe depends on z as well. Let's call it a of z. Okay, and again, we cannot assume it's just a real number. Anything that depends on z alone, just on z alone, will still be an acceptable antiderivative. Again, remember, take partial y, you still get y on the right-hand side, no matter what function in z is on the right-hand side. So at this point, let's go slow. What do we have so far as to what the potential is? F of x, y, z, we know it's made of x squared over 2 plus x, y, z. Actually, I'm gonna write it down underneath here. So far my potential is x squared over 2 plus x, y, z plus k of y, z, which right now I determine it's actually made of y squared over 2 plus some function of z. That is still to be determined. How we determine it? Again, finally by matching the third component of the vector field, which is z plus xy. So now we take partial z of xy, z, f of xy, z. X squared over 2 disappears. Partial z of the middle one is xy. Partial z of the third component is 0 plus a prime of z. This should match z plus xy. At this stage in the game, both x and y should cancel if you did everything correctly. So you're left with a prime of z equals z. And then finally we integrate with respect to z, and that gives me a of z, z squared over 2 plus a constant c. This time an actual real number because we integrated over all the variables. So now the potential matches all the three components. I mean the partials match all the three components, and we can finally provide the answer. So the function whose gradient is the vector field is going to be x squared over 2 plus xyz plus y squared over 2 plus z squared over 2 plus some constant of integration c. It's kind of squeezed here, but hopefully it's clear enough. And you can double check by taking all three partials to see that they match. So, and you can imagine that you can go on even with more higher dimensions, right? I mean, if you have a function of 4 variables, you can do the same thing. So as you can see, it tends to be a little bit of longer process in 3 dimensions, but the idea is the same, which is the reason why I typically don't put it in the exams. So I think that's enough. Just so you know, we're going to have 3 more sections. The next one, we're going to, so basically the last topic of Calculus 3 is going to be kind of what we did for curves, line integrals, but this time for surfaces. So we're going to study the equivalent of or the analogous to a line integral, but this time for generic surfaces in 3D, which leads to something called the surface integral. So the next section will be to learn how to represent a surface via parameters, the so-called parametric surfaces, followed by the surface integral, and then we conclude with two major theorems which relates these integrals, just like Green's theorem. So that's it for today.